Okay, so here we have data for our first deceleration curve, or one of them. And we started off with this function x of t equals negative t squared over 2 plus 15t. Don't worry about how I generated that, but this is a function that we're going to need to generate data for our first position time table. So we had negative t squared over 2 plus 15t. Again, this is a previous assignment. I think it's 2 assignments ago. The time interval was 0 to 5 seconds. And so now we start placing the information in for every second. So when t is equal to 0, we place 0 everywhere there's a t. So we have negative t squared over 2 plus 15t. Well, then that's going to be 0 squared over 2 plus 15 times 0, which is just 0. So at 0 seconds, the position is 0 meters. So that's going to be our first pair in our position time data table. When x is equal to 1, or time is equal to 1, we replace 1 everywhere there was a t in that function. So that'll be negative 1 squared over 2 plus 15 times 1. That gives us 14.5. And so we do the likewise for all the other times. T equals 2, 3, 4, and 5. And so these are our data points that we get for every time. So you're going to be doing something similar in your projects. Every person in your project is going to have a time data set, and you're going to generate particular points associated with those times. So one group might have 2, 4, 6, 8, another one 3, 5, 7, 9. You're going to all have different times, and you have to use the function here to get the points. So right now I'm using 1, 2, 3, 4, 5, our typical, data set 0 through 5. To get these data points, obviously 0 here, we go from 0 to 14.5, 28, 40.5, and so on. Okay, and then when time is equal to 4, we get 52, and time is equal to 5, crank, you get 62.5. And now with all those data points, we start generating our data table. This is our position time data table. At 0 seconds, we get 0 position. At 1 second, 14.5, as we saw above. At time equals 2, 28, 3, 40.5, 4, 52, 5, and 62.5. We can see that the gaps are getting smaller and smaller, and that's going to be key in our velocity time intervals. And so I had you that day. Yeah.
Sorry, can I, for the equation, where the negative t squared over 2 equals 15t, is just the t squared, or is the whole fraction squared?
Just the t squared.
Just the t. Okay, thank you.
Mm-hmm. All right. So, and then I had you go to breakout rooms and generate your velocity time and acceleration time data tables. Hopefully there's some familiarity with that, but if not, we're going to redo this as much as we can. So that's why your attention is paramount. Okay. So we know that the velocity points are going to be the slopes of all of these pairs of points. So if we're trying to find the velocity at the first second, what we have to do, or get our first velocity. We'll deal with where the velocity is on the VT graph later. So our first velocity would just be the slope between these two data points in position over time, because velocity is delta x over delta t, or final position minus initial position divided by final time over initial time. and those finals and initials will correspond to each data point successively. So we're going to see that right now. Velocity is change in position, change in time, final position minus initial, T final minus TI. And for our first pair of data points, we have 14.5 minus 0 divided by 1 minus 0. That gives me, well, 14.5 meters per second. Why is that? Because this is going to be a difference in meters divided by 1 minus 0 seconds, meters per second. So that's my first velocity that I'm going to be dealing with. Again, I will show you why and how to plot these points in a second. So our first velocity is there. Our second velocity will be the second data set. So it's going to be 28 minus 14.5 divided by 2 minus 1, and so on. 40.5 minus 28, 3 minus 2, divided by 3 minus 2, until we get all the way to 5. So again, okay, so I'd say 28 minus 14.5. I had that somewhere else. That's 12.5. Or I can't even subtract.
It's 13.5.
Yeah, 13.5. 13.5 meters per second. How the simplest operations become difficult. I don't subtract anymore. 40.5 minus 28. And these are all going to be 1 on the denominator. That's going to be 11.5. 12.5. See? Yeah. The next one would be 11.5 just by pattern. So 52 minus 40.5 divided by 4 minus 3. And you can notice something about the velocities. They're getting smaller and smaller. They're going from a large value incrementally downward, 13.5, 12.5, 11.5. Probably see the pattern. It's going to be a constant decrease. So the next one should be 10.5. And so as we see here, 62.5. Minus 52. Five minus 4. Okay, so those are all our data points for velocity. So you might be saying to yourself, is this 14.5 corresponding to 1 or to 0? Sometimes it's corresponding to 1, sometimes it's corresponding to 0. There's a little bit of calculus reasoning in there as to why. It's a little nuanced there. Of course, we won't talk about it here. But one rule of thumb, we can know, like this first data point here, is this 14.5 relative to 1 second or 14.5 relative to 0 seconds? Well, one thing to know if 14.5 is at the first second or at 0 is to notice something about the gaps. okay? If your gaps, or since your gaps here are decreasing, the first velocity will be at 0. My first velocity is 14.5 meters per second. That corresponds to the t equals 0. So a rule of thumb, if the gaps are decreasing as they are, the first velocity I calculate will be at t equals 0 seconds. That's just a rule of thumb. Keep life simple. Of course, you can complicate it to get a more thorough explanation, but it might just turn out to be complicated. All right, any questions on that rule of thumb there? Do you notice that the gaps are getting, well, I want you to see that the gaps are actually getting smaller and smaller because the object is decelerating. We know that that rule of thumb exists for decelerating objects, that the gaps get smaller and smaller. When it's accelerating, the gaps get larger and larger. Well, in this case here, it's decelerating. Gaps are decreasing, getting smaller and smaller. Therefore, the first velocity that I've calculated will be at t equals 0 seconds. That means that in my VT table, I've calculated these V's for all these T's. Okay. So 14.5 relates to 0. That's how we get around that whole business of is at 1, is at 0. At least algebraically, rule of thumb-ish, slightly hand-wavy-ish. Only relative to the full, thorough calculus explanation, of which I don't assume many of us are in calculus right now. So that's at 0. So 13.5 will be at 1. All right, so you just start, even if you have v sub 2, don't trip on that, because that means that's your second velocity. That doesn't mean velocity at t equals 2. That means the second velocity that you calculated. The second velocity I calculated corresponds to 1 second, and so on and so on and so on. Does that make sense? Or do we have a question? And it becomes easy.
If the gaps are not decreasing, would it be at 1 or instead of 0?
Speak up, please.
I said if the gaps are not decreasing, then it would be at 1 instead of 0?
Yes.
Okay.
But let me revisit that in context. So we'll get to that. So 10.5 will be 4, and then if we wanted to make a 6 second, obviously we can see the pattern and make this 9.5 at 5. So this is all you really need. Even though we have a data table up top for X versus T from 0 to 5 seconds. You keep things consistent if you like. You can make a slight 9.5 at 5 so that everything is uniform time-wise. Okay, so now this should be very easy to calculate acceleration, because acceleration is going to be the slope of all these data points, each pair. Okay. So the acceleration would just be a horizontal line because it's going to be a constant value. We'll see that here in a moment. So yeah, so we'll see that right now. All right, so acceleration, first acceleration or acceleration period is delta V over delta T. V final minus V initial. And I just think my speaker is acting weird on me. I couldn't hear you. Usually I can hear you clearly. So 13.5 minus 14.5 divided by 1 minus 0. So that's going to be -1. Right? So you guys could recall this from that assignment. I know many of you got that -1. So you know intuitively that the acceleration is going to be constant. You can pretty much infer that the other acceleration is going to be -1, -1, -1 for every moment in time. So it's going to be a straight line, constant. Constant deceleration, acceleration in the opposite direction, even as the object is going, well, away from the acceleration vector. So if acceleration is pointing west, your position is going east for a deceleration. And you also know that when velocity and acceleration are in opposite directions, the object is slowing down. We'll see that graphically. We'll see that the velocity points are in the eastern domain and the accelerations in the western domain. Graphically, we can see exactly that statement apply, that when acceleration and velocity are in different domains or different directions, that corresponds to slowing down. So A sub 2 V final minus V initial. So the more we see that, so it's going to be 12.5 minus 13.5. Over 2 minus 1. So the denominator always be 1. So again, that's -1. Pattern. You can start seeing a pattern. You know, usually in physics, we get to a pattern and we can predict the future. We can keep going. So A3 through A5 will all be -1. So just to, since we're here, let's prove that. Thinking about that last question. Okay, so that's going to be 11.5 minus 12.5, 3 minus 2, -1. Constant deceleration. And then also, -1. And then so we, for good measure, we put that 9.5 in there because we saw the pattern above. And you will always be able to just predict what the next one's going to be, even if like you've had data just to stop at 4, you can already see this is going down by 1. Okay, 9.5. Yeah, just throw it in there. And so that's 9.5 minus 10.5, 5 minus 4, -1. So again, okay, how does that look graphically? Well, let's generate our table and we'll do the VT. Well, we'll do all the points. We'll do, I'll have you graph it because I have to collect all this data and I gotta scroll back. But I guess we can do it first time. Usually have it on paper here, so I don't have to scroll around. So we got our VT, XT, VT, AT. And this is the pattern you're gonna, so get familiar with this. Get used to what you're going to do. You're obviously going to have different time sets for every partner, and you're just going to generate the same information. or similar information in the same way. You're going to create XT, VT, AT, everybody. Everybody's going to graph their own graphs, or position time, V time, velocity time, acceleration time graphs. You're going to do your own motion maps. You're going to then also do something with forces, which we just introduced. So, step by step. So, all right, so inferentially, I guess you can infer, you know that -1 is going to be the key for all time. So -1 exists at 0. -1 exists at 1. -1 exists. So it's -1, just a horizontal line of negative acceleration. -1, 2. -1. That's the easiest case. Okay, any questions? So again, this data table reflects what we already know, that the acceleration will be constant. In this case, negatives, other cases, positive. Positive, it won't change. And that very fact allows us to derive all of those motion equations that we use in our homework assignment there. Delta x, VIT plus 1/2 AT squared, 1/2 VI plus V final delta T. It's all based on the fact that acceleration is constant, whether it is negative constant or positive constant. Otherwise, we'd have to derive a whole new set of kinematics equations if the acceleration did change. And there are those equations. I'm just going to rough draw those curves. Actually, I'm going to do a new share here. And familiarize you with the old worksheet here. So, okay, hopefully you can see this. So all that data is going to generate this function for x versus t. The gaps are going to get smaller and smaller, and it's decreasing. The reason why it looks like that is because that is the graph of that function in the first place. At -t² / 2 + 15t is this graph. So when we plot the points, we're going to plot them correspondingly to the function. And it looks like this. And so now we put all of our data points for velocity time and then acceleration time right here. It's going to be negative. So again, it all comes back. It's reflects of different ways of, like, multiple ways of saying the same thing. I got a constant negative acceleration. That means I'm on the brakes. I'm slowing down. My velocity is going from a high value to a 0 value. I'm going from a 0 position to a large position, but my gaps are getting smaller. Even though I'm increasing position, the gaps are decreasing, corresponding to a negative slope or a negative velocity, or my velocity is getting smaller, and that means my acceleration is in the opposite direction. So that's what I was going to draw, but I'll go back and draw it. So xt looks something like this. Now, of course, you can put all your points in there, like the 14.5 and then and this is 0, 1, 2, 3, 4, 5. So you're going to do that in your full version. And then my VT is large velocity all the way down to 0. Of course, We didn't reflect 0 here, but you can see that it's going to trend down to 0 at some point. Maybe at t equals 10 or whatever. It's going to go 9.5, 8.5, 7.5, 6.5, 5.5, all the way until it gets to 0. So it's up to you. If when you're drawing this, you can leave this kind of hanging at 5 seconds because you know that your data table does not go all the way to 0. So you can do something like this. Okay, it's because at 5, it's not quite, it's like 9.5. And maybe at 10 or 12, it's at 0. But you know it's going to eventually get to 0. Okay, it's all up to you. Either way shows that the object is slowing down, that the speed is decreasing. At what rate? At a constant deceleration of -1. And you can say, quickly. And that's what we had on the previous slide. Any questions on that? Meters per second squared, and I'm gonna have you label everything. I want you to be as thorough as possible. This is a final exam, so thoroughness. Everybody get that idea? Do we see? Ask away, please, because I want to make sure that we have just a basic understanding. Yeah, there are going to be questions. That's okay, but do we see it? At least for the moment. For the moment. Velocities are getting smaller. Positions are getting larger, but gaps are decreasing. So now that I got thorough there, Rita, if the gaps are increasing, we are accelerating, we're speeding up. So at that point, your velocity will be 0 at 0 seconds. It'll look like this. It'll look like this guy here. Because now I'm on this side. I have a different function, I have a different relationship. So velocity will be zeros at time 0, and then it increases as opposed to over here. Gaps decrease. I start large at 0 and get small. Conversely over there. Those are actually, they're not reflections, but opposite physics. But okay, so we'll deal with that. But I believe with the gaps increasing, that's an easier case because we can start, everything starts at 0 and increases. As opposed to this, it gets kind of weird. Is 14.5 at 0 or is that 1? It's at 0. Okay, that's our first deal. Motion map. You would be drawing a corresponding motion map with this. And you don't have to get real fancy with the motion map. You're going to have something that for every position, you can put the positions down if you want, or just kind of arbitrate, something like that with 5 of those. And it's going to start off very large. You don't even have to make the markers. But it's going to start off very large and start to steadily get smaller and smaller. Well, I got too small too early, but it's going to look something like this for your motion map. Right? Because by definition of things that slow down, the gaps get smaller every second. So these little blips represent, these spaces represent intervals of time. 1 second, 2 seconds, 3, 4, and then 5. Something like that. So got a little too small there. But, and these numbers down here, you don't have to fill them in if that's a little bit much. But you know that if you were going to do that, that's this first marker here will be 14.5. You know, after 1 second, and then 13, and so on, or 28 rather, for your position time motion map. But to keep life simple, you don't have to label it. The motion map can be unlabeled. Let's see, what else would you have to do for this? Forces. There is a deceleration, you know, by Newton's second law. Even though there's a deceleration, it's still an application of Newton's second law because it's some kind of acceleration. But this case, the acceleration is opposite the motion of the object, but it's still acceleration. How would have you deal with this? Guess I'd have you put this into a graph as well. Make your life simple, huh? Trying not to get too complicated. The net force is mass times acceleration. Familiar? Saw that just a couple of days ago. Even though the acceleration is -1, the net force will be a negative number. Okay, it'll be a constant force for all time. The speed changes, but the force is constant because the acceleration is constant. What do we say? Wherever the acceleration goes, so does the force. The force is the dependent variable. The acceleration is the independent. Meaning that I'm going to be measuring the force based on what I got for acceleration, independent. So my force will be on my y-axis, my acceleration on the x-axis. Very similar to x equals velocity times time, where the positions that I'm generating in my measurement in my experiment depend on the times that I got, which is exactly what I did when I got my XT data table. I did it mathematically, I did it data-wise, and it's reflected graphically, which reflects it physically. So everything consistent. So I wanted to show you multiple ways of seeing the same concept, graphically, mathematically, motion map-wise, equation form, even we've done some problems in that aspect. So it's very key to be able to, have a well-rounded understanding. So if I was to reflect F equals MA in terms of all these graphs and stuff, I would do something like this. Jeez. Laptop is all skewed. Okay, force it's going to be for all time. Force versus time, I guess we can do that. It's going to be the same force for all time, but the force will be negative. So we can just say, come down here to the negative domain and just be, do something like this. F, force measured in newtons. Force measured in newtons is also constant because it reflects the exact nature of the acceleration, which is constant, even though negative. Whatever that force is, whatever this mass is going to be positive, because mass can be negative. It's say 2 times negative 1, the force is going to be -2. Do you see that? So this is what you're going to be doing for every partner, at least on this particular type of graph. There's another type of deceleration curve that that we can do. I just laughed right now because almost every day I see 11, 11. Not with I see 11s all the time. I heard something about that, and it's kind of mysterious. It's very interesting. It's a little uncanny. I've never saw one number so often. These last few weeks. But do you understand this stuff? I mean, well, any questions? Please take a minute to absorb and fire away if you have any questions.
I have a question. I don't know if this is just common sense. I'm just not connecting the dots.
Yeah.
For the Newton's second law, you drew the graph. Is there a table? What would the table look like for that? Would it look just like the duration time?
It would be very similar to the acceleration time, but I'm not going to have you do a table for the forces. Just a graph.
Cool.
Yes, because it's kind of redundant too. Because I'd have to give you a mass and then all that stuff. So.
And then also, another kind of dumb question. If this is the initial data you gave us, it was decelerating at a constant rate, so it's below the x-axis. If it was accelerating at a constant rate, it'd be above, right?
Yes, that's right.
And then if it was accelerating at like a nonlinear, so like an unconstant rate, then would the graph or the graph for the Newton's second law be different?
It would be totally different, but we won't deal with any changing accelerations.
Okay.
Because if we had a changing acceleration, let's say the acceleration was increasing, then the force would also be increasing. But for basic physics or introductory, we deal with constant acceleration, constant forces.
Okay, thank you.
Yeah, no problem. Perhaps at this time, yeah, I think I'll get you to right. I think I'll have you go to your breakout rooms, and I want everybody to do the similar stuff. Now, everybody in each group, all right, well, I'll randomize it. I mean, because it's going to take too much time to put you all in your regular groups. Have you guys see each other, and then, yeah, why not? Time is of the essence. So this is what you're going to do in your breakout room. Anybody seen that movie, Us?
Yes.
You know what I'm talking about then, Lala? Or do you remember what the number 11? And it's kind of trippy, but you know, in your breakout rooms, everybody's gonna have, okay, I think since everybody's gonna just be conglomerate, I will have everybody use the same function. Okay, we just used that to generate all those positions. So I want you to generate your position time. data tables and graphs for t equals 2. Okay, so we'll do that. So maps. Okay, that's all we're going to do with the same thing. Instead of 1, 2, 3, 4, 5, we got 2, 4, 6, 8, 10. Same function. Generate your data tables for XT, VT, AT, graphs, plot your points. That's all you do, your data points. Generate motion maps and force graphs. And make sure you have that. We'll come back at 11:45.
Mr. Kelly,
Somewhere around there. Yes, Sophia.
could you scroll up just a little bit, please?
Uh-huh.
Thank you.
Right here. Okay.
Yes.
Okay.
Mr. Kelly,
Yeah.
how do we generate force graphs? Can you like scroll up to when we?
So once you get your acceleration, whatever that value is, it's really going to be like the same thing. I'll tell you what. So let's say for a mass of 2 kilograms. So if I was to say, use a mass of 2 kilograms, and I know my acceleration above was -1 meters per second, then my force is going to be -2. So use the same mass, and so this number is going to be specifically -2 newtons. So that's how you would generate your force graph. It's going to be a constant force because the acceleration is also constant for any mass.
So do we use 2 kilograms when we make our force graph for the equation below?
That's correct.
Okay.
Going to be in random breakout rooms. Okay. Yeah, so I'll put in, let me put in like 4 to 5 people. Okay, create. Like 25 minutes. So, talk amongst yourselves, do all that, because this is actually like the first part of your final. Okay, and then you can share with your actual group when we start doing the final on Friday. All right, there you go.
Mr. Kelly, sorry,
Yeah.
I have just one more question. So that
Yes.
initial equation you gave us,